Welcome back. We are back on page 2 of the parametric packet, day 1 still, but this topic is just too good not to do a couple more examples as we're learning how to graph these equations. So here we got a graph. We talked about how there are advantages to graphing something parametrically over just rectangularly. We can graph a sideways parabola using its rectangular equation. We've been practicing with that, but this graph also tells you what's happening and when it's happening. It relates everything back to time. It's also an easy way to graph a non-function. Another interesting concept is presented in the middle of the page. I want to see if I can get these two graphs on the same screen. Take a look at this graph. According to these parametric equations that look kind of like the ones that we graphed in example 1 with some slight changes, right? This one says 4t squared, still has the minus 4 for your x component. And then in our y component for the one we graphed, we had t over 2. This one just has a y equals t for the y component of that parametric equation. Well, this is the same shaped graph, right? Two different sets of parametric equations can actually have the same graph, like this one and that one. But what's different? As you look closer and you compare the t values, you see that this picture is traced out much more rapidly than the one that we graphed ourselves. It took us 5 seconds to get around the curve all the way up to t equals 3, from t equals -2 all the way up to 3. Whereas this one's moving quicker. This one starts at -1, here's t equals -0.5, t equals 0, a half a second, 1 second, and by a second and a half, that object has reached the endpoint that we got in our graph. So the second graph we'll just say is just traced out more quickly, or we could say more rapidly than the one that we graphed. Considering t as time. So in applications, it's kind of useful to have these two graphs as options because we can have two different parametric equations to represent various speeds in motion at which objects are traveling along a given path. All right, are you pumped to graph another one or two? Because I am. I gave myself a little t-chart down here. I would recommend that for these ones that you graph by hand. You need a column for t, right? That should be your first column, the time. Then the x, the horizontal component, and the y, the vertical component. I'd fill this column in first, and you've got a guide given to you. They don't want the entire curve. They just want the portion of it from -2 to 2 seconds, if time is in seconds. So I say go with the nice easy integers, -2, -1, 0, 1, and 2. Let's find an x value according to this function and a y value according to the second part of that parametric equation. So start with the x's. I guess we're just supposed to double all these numbers. So double each value in the t column, 2, 4. Okay, that's looking parabolic. What about y? In this one, we need to take 4t squared plus 2. So 4 times -2 squared is 4 times 4, 16, plus 2 puts me up at 18 units vertically. Let's see if we see some symmetry. So 4 times -1 squared would just be 4 plus 2, and you would get 6. For the next one. Okay, 0. Take the 0, let's plug it into the y component. 4 times 0 plus 2 just gives me 2. And then I see some of these same values. If I plug in 1, I get 4 times 1 plus 2, there's the 6 again. I believe if I plug in 2, I get the 18 that we got for that first value. So let's see what this looks like on a graph. Now, I say it's probably most convenient to count by 2's for each tick mark. So I'm going to put 4 and -4. Or horizontally this way, and I'll count by 2's this way as well. So 4, and then we'll say 8, skip 2 tick marks, 12. This should be just enough room because you can fit 18 right above 16. So now we plot the points, right? That would be the next step. I'll use blue here. And we'll plot the x's and the y's together. So -4, 18. I would note the time when you plot it. So that's at time t equals -2. You've got -1, -2, 6. -2, 6. That happens at t equals -1. Then you have a vertex at 0, 2. So 0, 2 is t equals 0. And then here's your symmetry coming into play. At 2, 6, that's happening at time t equals 1. And then 4, 18 happens at the end of the experiment at t equals 2. Now the part that I dread, sketching a smooth curve. Hopefully yours looks prettier than mine. It ends at those endpoints. Don't give me arrows on the two ends. I don't want it going up forever both ways. I want it to deliberately end at those two values, and you're almost finished. Can you think of the one thing that we're missing? Well, a parametric equation needs the arrows to represent the orientation. And you have one of two choices here. Either the object's moving this way, and you'll go, I guess you could say counterclockwise, or you're going the other way, clockwise, like the last example. How would we determine that? We'll go in the order of time. Since as time increases, you're moving from left to right on the graph. Let's put the arrows here to represent the time moving. So this is a good representation of the plane curve on the interval -2 to 2. And your arrows, the curve starts here at -418, it's going to end at 418. So two parabola graphs that we've constructed. 3 doesn't have any components squared. It just says x equals t and y equals -2t. So this should be a pretty simple table to construct for t, x, and y if we want to try this. Let's do, I guess we've got the same interval in this example. So let's go with all the integers from -2 to 2 inclusive. And the x's are just the t's, correct? So just recopy that column. X is equal to t. And y is equal to -2t. So we'll take each of these values and multiply them by -2. So how about 4 and 2? 0 times -2 is 0. 1 times -2, and then 2 times -2, -4. This one isn't looking like a parabola. It's looking like this thing is just falling from left to right. Let's sketch the x, y coordinates of those points, and then we will label them with their time values too. So -2, 4. I think for this one we can just count by ones. So -2, 4 is at t equals -2. -1, 2. So we are sloping down. T equals -1. 0, 0. T equals 0. At 1 second, you're at 1, -2. T equals 1. And then at the second, you're at 2, -4. So t equals 2. You have a line that is, like we suspected, falling from left to right. I completely missed some of those points. That was terrible. So not my best work. Hopefully yours actually goes through the points. I called it a line when it's really a line segment, and the orientation should go on there too. And we notice as time increases, you're moving from left to right. So you've got a good sketch of a line that comes from a parametric equation as well. All right, till next time. Have a great day.